I hate.
Actually 5 years old.
Yeah.
No!
Don't tell him. He didn't listen. Don't tell him.
I checked. I'm trying to see why you're wrong.
1A is like, it's like the division of
I hate
plan.
Give me the number.
No, it can sometimes.
It's the south direction.
Give me the number.
Max, did you write off with my bones?
One would be worth A. Oh, that's
It's just
negative
not
0.43.
because it's my blood.
My bones.
I'm sorry.
You're
Jeez, Bryce. So wrong.
Math time? Okay, am I actually a dumb person?
Oh!
The math.
Alright, here we go. Visual concept.
Visual.
Everyone listen up here. We got 3 types of collisions. We got inelastic, we got perfectly inelastic, and we got elastic collisions. So which ones did we do yesterday? Perfectly inelastic, okay? And really perfectly inelastic and elastic are your 2 extremes.
Inelastic collision. The objects deform and they move separately after the collision. The total kinetic energy decreases. During a perfectly inelastic collision, the 2 objects stick together and their final velocity is the same. The total kinetic energy decreases. During an elastic collision, the objects bounce apart and move separately. There is no change in the total kinetic energy.
Did you notice that when these 2 spherical objects hit each other, that there was like a deformation for a second, and then they went back to their original state? That's why it's called elastic collision. In the other 2 ones, they were deformed and they were permanently deformed. That's why they're called inelastic, because there's no elasticity to them. Does that make sense? Okay? So you're probably going to want to write this down somewhere. We're going to kind of summarize really the 2 extremes here. Alright? We're going to summarize just elastic. I should probably say perfect. Well, yeah.
We'll just do perfectly for me.
Okay, so we're going to kind of, these are really our 2 extremes. Now, like all the things we've talked about in physics, neither of these 2 are actually realistic.
Wait, haven't everything we talked about in physics been an extreme?
Pretty much.
Great.
Wait, so, you know
What?
Can't wait to use my dollars in this class in your life.
You can, yes. Stop.
Once we get into advanced physics.
Why is it elastic realistic?
All this will be
Why is
nothing
what?
until we
Why
get
isn't
advanced.
elastic realistic?
Advanced physics.
I'll explain. So it's never perfectly elastic.
Yeah, I should say, when I say elastic, I am kind of referring to perfectly elastic. That's true when he says that. So we assume that in a perfect, a perfectly or an elastic collision, it turns back into its original. Did I spell it?
Yes.
Yeah.
Origin AL.
Okay. Alright. It returns to its original shape. So at some point they do deform, right? We talked about the 2 things that collided that did deform a little bit, but then they went back to their original shape because they were elastic. Does that make sense? Okay? Then we said in this particular situation the kinetic energy is conserved. But the only way the kinetic energy is actually conserved is because we're making an assumption. We need to get rid of your notes. Because you are a lot quieter.
Yeah, start
I might just do that next. I might just do that
No,
next.
I did not pay attention. I had to write
Also, I couldn't read my notes. I guess it doesn't matter.
Okay? So kinetic energy is conserved because we're going to assume a few things.
Dissipation. I don't know, like this.
Dissipation?
Cause that, yeah, cause it's 2 valves.
Dissipation.
Yeah. Dissipation.
It's not always the case. It's not always the case that you have to have the 2 vowels or two consonants, but.
I mean, you spell Mississippi with 2 S's. Mississippi would be with 2 S's.
Mississippi.
Anyways, I'm an awful speller, you guys know that, so anyways. Okay, so give me an example of something that is elastic, that we know isn't completely true, that kinetic energy is conserved from a real life standpoint.
Golf ball.
Golf ball. Okay, on a hard surface. You know what you're saying? Okay, so if I take a golf ball and I drop it down on a hard surface, there's no deformed golf ball or deformed ground, right? So why doesn't the golf ball come back up to its original height?
It makes sound, acoustic energy.
Okay? The reason why it doesn't come back to its original height is because some of the kinetic energy that it has got lost or dissipated in another energy form. And typically the energy form that we're most probably familiar with in that context is what?
Dissipation.
Sound energy.
What is dissipation?
Lost, loses, dissipates.
Would there be
Oh, so those
deformed?
3 things lost.
Yeah. So like, there's probably also when it hits the ground, there's probably a subtle amount of friction, right? Well, friction we know is going to cause some heat transfer. Now it's probably not that much in the context of a ball dropping, okay? But there could be some other collisions where that might become a significant portion of energy being lost. Yes.
So like in a vacuum, a golf ball would bounce for a lot longer than if you were dropping
Yes.
a rubber ball.
Wait, wouldn't it just never stop that?
It would never stop because you still would have the friction with the ground. You would still have some energy getting converted into internal energy. Very little, but over time, yes. In a vacuum, a golf ball would hit and bounce up, and it would stay bouncing longer. Yes.
So it'd be the same with a bowling ball on a hard floor? Does that count as well? Because you're assuming no sound energy?
Yeah. Yeah, a bowling ball would bounce higher in a vacuum. The reason why a bowling ball doesn't bounce as high as a golf ball is its mass, and so what ends up happening when it hits the ground, it makes a louder noise because it's got more mass, so more energy is lost in the form of sound. Okay, and we're not thinking in a vacuum, so there's more air resistance on a bowling ball than there is a golf ball. So. Right, for example, if we were to drop a bowling ball and a golf ball in a vacuum, we know they would hit the ground at the same time, right? Okay? So, and if we're also in a vacuum, we have no sound energy dissipating. And yes, a bowling ball would bounce a lot higher in a vacuum.
Would they bounce at the same time?
If you drop it this high.
Yeah, you would expect that. There's probably a little bit more friction with the bowling ball hitting the ground, probably a little bit more internal.
Wait, isn't there still only like one contact point though on a bowling ball? If it's like round?
But not if it's if there's, even though it probably doesn't appear that elastic, there's probably some elasticity of a bowling ball. And so when it hits the ground, there is some elasticity that's going to cause more surface area of contact. Does that make sense?
Yeah, I want to know how high it bounce.
Like in a vacuum?
No, just like
Just drop it.
Maybe see. Okay? Then perfectly elastic is when the two objects what? They collide and, well, these are all collisions,
They
but
collide.
they stick together essentially, right? And we can treat them as the final velocity is the same. In this context, we're having two objects collide and leave each other independently. Okay? So in this case, we could say they stick together, and in order for them to stick together, they have to what? Probably a really broad question. They have to be formed.
Oh.
Deformed.
Real warm.
Now in reality, kinetic energy is not conserved in any of these things. However, we're making an assumption that that kinetic energy is conserved over here because we're assuming no dissipation. The reason why kinetic energy is not conserved
Also, would it just be because like there's only one kinetic energy that like mass is defined, so there's only one equation, and velocity squared, so it doesn't matter as much.
you still have twice the mass.
Yeah, but twice the mass, but like one velocity, like velocity squared equation.
Yeah, but if I were to do the two separately, then you
Oh.
would still use two
I
separate velocities even though they're the same.
Okay.
And so you would, essentially, you would take two numbers, when you multiply them, you're still adding the two together to get this. Does that make sense?
Yeah.
So like if I have, I don't know, 5 times 2 plus 10 times 2, that would give me what? 30. Versus taking and adding these two together,
Yeah.
15 times 2 is still 30. Alright. Now, on a test question, why did I do that?
Why did you do that?
Okay, on a test question, you're going to assume,
Can you please finish that out?
He doesn't understand. No, our no.
Left side. You go
Oh, left side is like the
Right side. Just give her the right side.
And what about that?
Oh, that's-
Okay, that's fine. I can live with that.
It's like a little.
so on a test, even though we know both of these are false, and kinetic energy is not going to be conserved in real life in either condition, on a test you're going to assume that this one kinetic energy is conserved, and that this one kinetic energy is not. Yes?
If it's never the case, then why do we say it is
Yeah.
the case?
To make the math easier.
What does it mean internal energy increase?
It is. It is. But we also talk about why it's not, so we know it's not. So it's not like,
Yeah.
it's not like we don't know it.
Yeah.
And because we do it the other way, therefore we assume that it's not the case.
Equals MC
In
squared.
reality, we know it's not true. If that makes any sense.
Well, it's just like we're doing it wrong.
Yeah, I get what you're saying. But this is actually what happens in a lot of the science classes, even in chemistry. Like, I taught you the octet rule. That doesn't happen. That's like, most of that is a lie.
Yeah. Come on.
Okay, and when I explain the atomic model, or what the atom looks like, most of the time I use the Bohr's model, which that's not the most accurate model. But it does a better job of explaining the idea than the quantum model does. Does that make sense? And so, the reason why is a lot of times I'll give you things that aren't completely true, but it gives you enough information to have a broad, big picture idea of what's going on, so that if you continue going on, you can say, oh wait, this is not true, and it's not gonna be like, oh my gosh. But you know what I mean? But because you learned it wrong, you still can easily adjust to what's the correct way because you know enough of it because you looked at it from a big picture standpoint. Does that make any sense?
Yeah.
Like, if I were to just go in and start talking about how the octet rule is not a thing, you'd probably be way more lost than having known the octet rule and me say, it's not a thing, and here's why.
He's being
Does that make
deceitful.
sense?
Lying.
Right.
But it's for
What
better.
does it mean, Pt2?
Mr.
Is
Chris.
sitting ever a benefit?
Internal energy.
So when an object deforms, energy actually gets converted into the object itself in the form of changing the bonds and changing the makeup of it. Because if you mess with the shape, you're changing you're changing energy. I wouldn't get too caught up in that. That's a pretty difficult concept.
Just memorize what that says.
You don't really have to memorize that. It's just an idea that we want to talk about.
And then also,
I don't.
is momentum conserved and perfectly inelastic?
Yeah, we're going to say momentum is conserved in both situations.
But then, perfectly
But you could probably also say that momentum isn't actually 100% conserved, because if kinetic energy isn't conserved, velocity isn't conserved, if velocity isn't conserved, neither is kinetic energy.
So this one has been conserved, this one doesn't.
We're gonna treat both.
That's actually the only reason.
Alright.
That was like number one.
Mr. Kramer?
Yeah?
What's internal energy?
Good question. So, that's a hard one to explain real quickly. What internal energy is the energy associated with the bonds and the structure and the makeup of the shape of an object. And so when you deform it, you're changing bonds, you're changing the energy.
So, over the time, if you were to bounce a golf ball in a vacuum, it would have the chance to break.
It would eventually deform, yep. Yep, that's why they try to do the, what do they call that, where they try to get something that continually works forever, and they've never been able to do it, because everything they use eventually, like they try to use magnets to keep things going on forever, and they can't do it because magnets eventually wear off and break down, because of the second law of thermodynamics, the entropy law. So it's not possible to ever get something to go on forever. Because in the end, it all eventually wears down, breaks down because of entropy. Because of sin. Okay, let's do this guy. Alright, Lauren, give me a variable up here.
Is there not an equation for
The
us?
first mass is 1.5 of the marble.
Say that again, sorry. He just asked me.
I'm sorry.
The mass of the marble is.
Can I just say M1, is that okay?
That's me.
Well, I'm sorry, I'm trying to ask, soon after.
Is this the same equation as yesterday?
Yes. So, and guys, you know, the new equation that I gave you yesterday, no, sorry, it's not the same as yesterday. It's not the same as yesterday. The new equation I gave you yesterday is just a modified version of the conservation momentum equation. It's the same equation.
Really?
It's just modified.
Okay, so you make masses one.
You could have used the first equation to solve the problem we did yesterday. You could have.
I see it now.
That's why I didn't pay.
Could this be?
But if you know that in certain situations to do, it makes it more simpler if you just use that more simpler. If you use the modified equation, it makes it less math if you know when to use it.
So you're gonna give us a modified version?
No, this is going to be just the same conservation momentum equation that we've been using.
So it's not the.
It's not the modified one. Yep. Okay. You said 0.015? Yeah. Okay, Jesse, could you give me another variable?
Yeah, mass velocity initial from the first one is 0.25.
Is there any direction that we need to know?
It's positive.
Okay.
To the right.
Cheyenne, could you give me a new variable?
Yeah, mass, the second mass is 0.037. And its velocity is negative 0.1.
That's two.
You said negative what?
0.18.
Okay.
So these are marble points before or after the collision. That both points are in the frictional surface.
Now I would say making the assumptions that we're making probably doesn't have a significant difference in if we were to do it, just actually taking all of these things into consideration. So why not just do it the easy way, even if the answer is not going to be that much different? That's essentially what they're saying with this, is if you do keep all the friction and all that stuff the same. You remember when we did the free fall example, when we used the picket fence and we dropped it, and we tried to figure out the acceleration?
Yeah.
Even though we weren't in a vacuum, it was still really close to 9.81, wasn't it? It was. So air resistance sometimes doesn't make as big of a difference as you might think. And friction doesn't always make a huge difference. So doing the assumptions makes us do these problems a lot easier and not give us a significantly different answer. Now, if you were trying to create a standard, you'd have to do it the perfect way, right? But if you're just trying to get a general idea, then using the assumption version is fine. Okay? Anything else up here that we need to know? Anybody?
Yeah, the final velocity is.
Is that the first or the second?
First one
Is what?
is 0.315.
It's negative, right?
Yeah, right.
Yes. I thought we didn't have to put the negatives there.
Okay.
I'm getting so confused because.
Listen. Maybe I should have not have ever said that, but the reason why I said that is because in certain situations it's okay because of how math works. If you do multiplication and division, the negatives don't have an impact on the value of the magnitude. But when you're doing addition and subtraction, you cannot get rid of the negatives because it changes the magnitude of the number. For example, if I say -2 times 2, what's my magnitude? It's -4, but it's still 4. If I did 2 times 2, it's still 4, right? It just doesn't have a negative on it. The magnitude's still the same, right?
Oh my.
But if I do
word.
2 plus 2 versus 2 minus 2, are they the same magnitudes?
Oh my.
So when you're doing a math problem that has addition and subtraction in it, you cannot avoid the negatives. But if it's all multiplication division, you can avoid the negatives because you're going to get the same magnitude, and if you pop a direction on at the end, you're fine. Does that make sense, everybody? So I'm hoping you were paying attention so we don't have to like say that again. I feel like I've said this quite often. Okay? So now we've got we don't have any zeros, so we can't cancel anything out here, can we? So we gotta use the full equation. Not two. Yes, two. Yes. You okay?
Not two. Yes, two.
Sorry, guys.
That could be a rhyming.
Wait.
Can I do this right? Okay.
Not two.
Now, which variable are we solving for in the context of this problem? VF2 or V2F?
Yeah, I'll land it right now.
Yeah.
Let me check.
You want me to put all the numbers in, don't you?
No. I do.
No, I'm saying I just like it.
You're right or wrong?
I like it VI2.
It's just
I can't please everybody.
yeah.
Okay? So, how would I solve this particular problem?
You get rid of all the guys.
Okay, you'd have to bring this over by subtracting it and then divide by M2.
Yep.
So I'm going to try to not erase everything.
Just change the equal sign to a subtraction.
You're good.
Oh my word,
That
Emma
was
is the new
amazing.
Albert Einstein.
That's critical thinking. That's why I teach you this class. That is literally, like, I could care less if you know everything about physics, but critical thinking, that's what I want. Critical thinking.
Nice!
Why do you always change the equation first?
Because I think it's less work to not have to write all the numbers all the time.
Because then you just plug and shove.
Because then once you have it now you plug and shove. But yeah, essentially.
Yeah.
Kramer,
So just to me it saves time.
I don't think I'll ever do it that way.
It's fine. That's totally
That's
fine.
different answers than both of us.
What do we get for an answer? Anybody?
Both of the right sides is final.
Yes.
So I did have my note card wrong, and I still had to change.
See, I've seen like quarter answers.
Why are we at the end of the packet?
109, okay, yeah.
Big.
Should it be M2?
No, it's 109.
No, it's still.
I changed this. This is not the original equation. So don't.
No, I know. Should it be M1 V?
Big what noodles? Why am I so weird?
What do you mean? What do we get for an answer here?
109.
How do you know which direction it's going now?
Under a microscope.
Okay, well, I would look at the context of the problem.
What if it's
Does the math give you a positive or a negative?
Positive.
It gives you a positive, so it has to be in the positive direction.
So it's probably to the right.
Which means
because we
it's
have
to the right,
left.
yep. Now, you could probably look at the problem and think in your head what's actually going to happen here, and you might be able to deduce that as well. But, so you said 0.09 meters per second, and you should say to the right.
Yeah, is that right?
Is that right? Yeah, it's 0.09.
So does this count?
Oh my
as
word.
elastic
The first I did it wrong, and I did it right.
First I did it wrong, but then I.
This is probably elastic, yeah. I did it.
Marbles?
Yeah, I keep getting
Is
negative.
it marble or two marbles or
Two
what?
marbles sitting and then down.
Yeah. Yeah.
Because those aren't going to deform at all.
I also did.
Yeah. So
Did
then,
I say elastic?
yeah.
Yeah.
What about inelastic?
Inelastic, you're always going to have deformed.
Are we ever gonna have like an inelastic problem that's not perfect?
No, I do perfect, probably, yeah.
Oh, yeah, that's
Okay? Now, it also wants to know another thing here. I think, right?
No.
It doesn't? Well, I want to do it.
Okay.
Kinetic energy conservation.
I want to prove that kinetic energy is conserved here. I'm going to get rid of this.
How did you know?
Yep.
I got 0.02. That's what you guys got too. What? How did you guys get that too?
What is
Me and
it's
Bryce
point, you still got it?
Yeah, even up.
I keep getting it too.
Just even doing the point first.
Maybe you're bad.
I got the right answer, that's why you went to write the equation first.
Well, other
I
people
did
got
it
the
both
right
ways and
answer.
still got point.
I finally got it.
0.09.
I finally got it. I just,
That and grab that. And then I did them separately and grab the other stuff.
Why do you clear your history?
I do after every row.
What?
It's like habit, yeah, just,
Why?
I don't know, I've done it ever
Because
since
she
like
I want to know what she's typing.
freshman year.
Oh, you're missing a negative, guys. You're
What?
missing a negative.
The negative inside of
You're
the
missing a
negative
negative
point
on
eight.
0.315.
Oh, that makes sense.
Wait, which one needs to be
Stop.
negative?
Secretly I'm marking on that.
That's your problem.
Your problem,
Just had to
Steven.
get the
Can I have this?
Oh, it's to the left, I got it, okay.
It doesn't need.
Please look at my note card. Do I have this one?
Yes.
Second one?
You never
I cut you off.
Hey, Bryce.
Are you? Whoa. That's
I'm not sure I'm gonna get
Wait, what? What are you talking about?
I was gonna ask if I could.
I don't want to say somewhere, but
I could just cross it out. I
Big fat bun.
Don't worry, I just saw it.
I did actually. No. That's a very
Oh! You loaded that. The book was falling.
Are you sure I last round?
She sent me a screenshot of something and it said 1 hour and 55 minutes. Yeah, Shy goes, that is so long. I was like, every night.
Stop. No, right.
Yeah, no, we've been on the phone for like 5 hours.
3 minutes to
I don't time my short, you just lift up. I don't always time my short. That's so much better. It is.
I don't wear boxers, so no. I also hardly wear boxers. Also, that's just weird.
It takes like
You don't have a minute to stop.
I wear a Hanes, so I can do that like.
I also don't wear
I'm
How long did you
like 3 minutes. Yeah, but I don't go to, like, if I wake up in color at 7, I don't go to bed at 7. If I went to bed at 9. Oh, my God.